Hello friends, welcome back to my channel, and in this session we are going to talk about the interesting topic, which is semantic data chunking in the RAG pipeline. So building a context aware RAG pipeline using semantic data chunking. So let's get started. So before we start, this video is just a continuation of this AI generalist playlist. So we started very quickly with the initial steps of data collection for the RAG, different type of sources of data, and then converted different sources of data into Markdown, and then data cleanup and cross-source deduplication. And also we have started with the initial types of data chunking techniques. And in continuation to that, so we will see this semantic data chunking details. Also, before we start, the theoretical part and the code is available in this GitHub repo. This link is in the description. So in this S05, here there is a source code, both for development and for automated testing. And for this particular data chunking, we are going to consider this PDF file where there are various sources of content. So this is a PDF file, and there are it's a technical documentation basically, and there are paragraphs, there are section breaks, then there is a diagram, there is a picture, then there is a section subsection, then there is a table, and again some diagram, and so on. So it's a mixed source of information, so that will be helpful for showing the demo. Okay, right. So let's get started. So semantic data chunking. So some theoretical parts. So it's a critical processing step of splitting large documents into smaller, manageable, and semantic pieces. This allows the retriever, the retriever to efficiently find relevant info and fits within the LLM's limited context window, improving the accuracy and reducing the hallucination. Right. So key aspects of purpose, strategies, overlap, and impact. So we can uh, go into this by reading this text, but I'll just skip this for now. Right. So semantic chunking. So it uses embedding model to calculate the meaning of sentences and only splits where a topic shift occurs. Okay, so it is more accurate than rule-based methods, but requires more processing power, obviously. So rule-based methods are basically, splitting the document, splitting the input data into fixed number of characters, or recursive character splitting, or sliding window type, and so on. So it's based on some kind of a rule. Now, in semantic chunking, the technique is to have, where the topic shift occurs. So it's based on the topic. So in this, it is more accurate. Okay, it is more accurate, but it needs more processing power. Obviously, there is a benefit of it, right? So it ensures that the context provided to the LLM is thematically coherent. Okay, this is important. It is coherent. Then, unlike fixed size splitting, semantic chunking groups text based on vector similarity. By identifying where the meaning changes, the system creates chunks that contain complete concepts. Okay, so it's a meaning based, or there's a topic shift, so then it is split. Okay, just a overall picture. So there is a input source of data, let's say some PDF, doc file, Excel file, or whatever. So it creates the embeddings, then embeddings generation. Okay, then internal step that is called as measure similarity, then create semantic chunks, uh, detect uh, topic shift. So there is a topic shift, so then change the uh, chunk, and then we have something called as cosine similarity. We will see this in a bit. So detect topic shift, and then measure similarity after the topic shift. Okay, so let's proceed. So step by step we will see. So sentence splitting, the document is first divided into individual sentences or similar units, often using tools like Python libraries like NLTK and Spacy. Embedding generation. So an embedding model converts each individual sentence into numerical vector. Okay. Similarity measurement. So the algorithm calculates the cosine similarity between the embeddings of adjacent sentences. Okay. Breakpoint identification. So a significant drop in the similarity score. This is important, similarity score. Okay, so in the earlier slide, measure the similarity and measure the similarity. So there's a scoring involved in it, and the one which is matching higher side, that will be chunked together or placed together. Okay, similarity measurement, cosine similarity between the embeddings of the adjacent sentences. Breakpoint identification. So a significant drop in the similarity score between the consecutive sentences suggests a change in topic, marking as a breakpoint. Okay, then chunk creation. So sentences are grouped together until a breakpoint is reached, ensuring each chunk maintains internal semantic consistency. So this is a bit of a theory, okay, and we need to understand why the semantic chunking is a bit popular because of this all, the internal steps, right? So um, where is this useful? Okay, so the traditional technique where it is fixed size chunking or whatever. So semantic chunking is more useful in this situation. So legal contract analysis. So if you have done any rent agreement or any merger and acquisition between two companies or any legal document, okay, so it needs references in multiple pages, and let's say you are on page 20 and then there is a reference of something which is on page number 2, 3, 4, 5. So this kind of situations we need to have semantic chunking, it fits better. So legal contract analysis is essential for keeping a liability clause and its specific, except in cases of whatever exclusions in the same segment. Okay, so bit of complexity here. Medical diagnostics, yes, very good chance of having complex items mentioned in the report. So crucial for ensuring a patient's medication list remains attached to its associated drug interaction warnings. Okay, academic and scientific research, yes, lot of complexities, lot of cross document references and all. So necessary for dense papers where topic shifts occur frequently and settle within long paragraphs. Then other things like technical troubleshooting manuals and financial compliance and auditing. So wherever there is a good amount of complexity, good amount of multi-document or cross-document references, then semantic chunking is very useful, right? So let's see one simple demo. Okay, so source code is already there. The link is in the description. So semantic chunking. Okay, so if you see here, here I have involved this Olama embedding functionality. So here the embeddings or the chunking will happen with the help of Olama AI model. Okay, so we'll see this in a bit. So Olama, just to show you Olama. Olama is one of the very good and very handy, and of course almost free tool where we can use their cloud models, AI cloud models, or we can download it on local, and we can also use local models also. So based on your system configuration. Okay, so I have logged into Olama and I have good amount of credit. So they give the AI, they give the credits, number of tokens, basically whatever we want to process, either via this prompt, either via this UI or via API. Okay, so here we will use API. So Olama, I'm running it on my local. Okay, so the URL will be this. If I'm referring any locally downloaded AI model, and if I'm using something which is the remote AI model, then I'll have to use this URL. Okay, and for local AI model, I'm using this nomic embed text. This is a very popular, very highly suggested, highly specified AI model for embeddings. And for cloud, I'm using different AI model. Okay, so for now, just for embedding, I'm using only this embedding model. Okay, and I'm using this from the locally downloaded AI model, right? Right, so I have this document, which is this conference document, which we have seen. This is the conference document. I'm going to generate the chunks using semantic uh, technique, semantic chunking technique. So first thing is I'll load the PDF file. Then I'll join all the pages to have every text combined. Then I will be using this nomic embed text AI model, and I will have an object ready for this Olama based embedding. Okay, I need to pass the model and base URL, and that's it. Since it is a locally downloaded AI model, so I don't need to log into the actual Olama and then pass on the API key and so on. So it is basically locally downloaded, right? Um, then I'm using this semantic chunker method. So semantic chunker, which is there in LangChain experimental package, it splits text based on semantic shifts detected by Olama model. Okay, so I'm passing this particular object. Okay, and the um, um, percentile, 95 percentile, what do you say, similarity matching. Okay, so I have this object text splitter, and then I'm going to use this method perform chunking, which is create documents, and I'm going to pass the full PDF content. Okay, so then I will into return chunks. So these are the chunks which are based on the uh, semantic model, a basic simple model, and based on the chunks we are going to validate further. Okay, we are going to use those chunks further for user query. Okay, so after that I'm just going to iterate through all the chunks, and I'm going to just print the chunks here. Okay, the for every chunk I'm going to just print the first 600 characters, because the document is huge. Okay, document is huge, so whatever chunks are getting created, I'll use, for now I'll just print the 600 characters, maximum 600 characters per chunk. Now because it is using this AI model, locally hosted AI model, which is this nomic embed text. So local processing has limitations based on the local laptop which I'm using, the power of the laptop, the RAM, and all those things. So it might be a bit slow. Okay, right. So if you see there are chunks generated, so I'm just, for the sake, I have just printed the first three chunks, and each chunk only 600 character. Okay, right. So if you see, the chunk is a little bit bigger. Okay, uh, the text is probably, like, most of the time it is relevant. Okay, and um, it is coherent. Okay, it is coherent, right? Fine. So this is about the semantic chunking example from the development perspective, like how the developer will typically develop this. Okay, so they will take, for whatever their requirement, they will take this data and then convert it into semantic chunking, and we will be able to get the chunks, right? So okay, so before proceeding, because this is the developer part. Now, from the being from the automation or from the testing background, I need to confirm that whether the chunks are getting created as per the requirement. Okay, so for that I have this QA related item where I'm going to validate or evaluate whatever chunks are generated, whatever architecture or development done by the developer, whether the chunks are coherent, and really it is the way semantic chunking should happen. Okay, so this is the automation code, and see, if it is if the data is very small, then we can manually create some validation data. But if it is huge data, then we have to automatically generate the test data and also do the validation. Okay, so that is why this all um, efforts to do automatic testing. Okay, right. So again, I'm using the same PDF as a data source, again the Olama this thing, and here if you see, for embedding, I'm using this nomic embed text model, and for the actual validation, the automated validation of the semantic chunks, basically QE of that, so I'm using this again a different LLM, which is GPT OSS 120 billion parameters. So it is fairly enough uh, parameters to validate a particular semantic chunking implementation. Okay, so right, so I have this Olama model, which is using this new cloud-based AI model, and it's the same normal embed chunking. Okay, right. So we need to make sure that the Olama is running. Okay, you have to log in and it is running, and Yeah, local Olama URL is this fixed, okay, and for remote I'm going to use this exact URL. Then, right, so next step, so dynamic synthesis from chunks. So create semantic chunks first to ensure context are not empty. Okay, so I have to read the input data, and then I have to create the chunks. Okay, I have to create the chunks. So same thing what we've done here. This is at the end. What we have is we have chunks. So same thing. I'm going to generate the chunks. Okay, next step. So generate the goldens using Olama objects directly. So what is this golden? So what we are going to do is we are going to pass on this file content to this Olama, the bigger Olama model, and we are going to ask to this Olama, give us the golden set of expected output versus the actual output. Okay, and that is what we're going to verify. Only thing is we are going to have the reference as these chunks, semantic chunks. Okay, so the technical step is we need to have a synthesizer, then we need to build the context, and then synthesizer dot generate goldens from the context. Okay, and we need to pass the synthesizer and context objects, and some technical things. We include expected output true and max golden per context is 1. Okay, we can play around with this, but this is a simple example. Right, now automated validation. So create a retriever from your semantic chunks. Okay, so we again some technicalities. So doc array in memory search for semantic chunks and the embeddings. So we will have a vector store, and then vector store as a retriever. We will search for this k equal to 1, k is to 1 parameter. Then contextual recall matrix with the threshold of zero point 0.7 and model is my LLM. Okay, so again these are technicalities. Now we will do enumeration. So for each set of goldens, we are going to verify that the the retrieval is matching with the expected output or not, and we are going to have a score. Okay, recall metric dot score. So that typically if the score is let's say 95%, above 90%, it is considered as good match of the actual and the expected output. Okay, now let's run this. So I'm going to put a breakpoint here, so I will be able to know what are the goldens. Okay, the um, references for semantic chunks validation. Because it is going to talk to the remote Olama model, so there is a delay. Okay, so generating goldens using Olama LLM and embeddings. Okay, so this is probably the 100% cloud-based or cloud AI model-based testing, but definitely there is a chance that we can have human in the loop where we can verify the expected and actual goldens, whether they are really they really matter based on our experience, and then we can proceed. Okay, so the goldens are generated, basically the references. You want to evaluate the goldens, and if you see there are 4 goldens generated, we can go for additional key value pairs. Okay, now so let's take the second example 012. Okay, just for the sake. So based on the document, uh, there is a context, there is a expected output. Okay, so why this is required? Okay, as I said, if the document is huge, okay, if the document is huge, we cannot manually keep on raising the questions or raising the queries, and then we verify the actual answer which is matching. So it's a debatable point, of course, and it is also not suitable for a bigger document. Okay, let's say there are 100 pages, so for each page for each important topic, it's not possible to do manually. That is why it is done programmatically, right? So there are four queries, four question answer, like expected and output, expected and actual considerations generated, right? So that we are going to verify now with uh, the actual data what we have. Okay, right? So let's run it. So we will see the recall whether the retrieval of the question, retrieval of the answer based on the dynamic question, is it correct or not, is it matching or not. Okay, so how do we use SMS, OTPs and Firebase FCM push notification? So retrieval is 1.0, so it is basically into 100, so 100% match. Okay, question 2, 100% match. Okay, question 3, 0% match. So compare IMS's strong consistency, Redis reservations with user services model and expiration behavior. Okay, right. So no match found. Okay, question 4.8. So 80% match. So if you see, two things are okay, but this is completely not acceptable. It is 80% match. The answer is the recall is 80% success or 80% score, which is still okay, but again there is a chance to improve on it, right? Okay, so what we have seen is we have seen the actual algorithm or the actual implementation part and also the QA part. Now, of course, there's no. This is again one example, and it's not the fixed approach, but one of the simple and basic approach. There's a still room for improvement. Okay, and it can be extended further. Right. Now let's proceed, and we'll see some bonus. Okay, so what we have discussed and seen so far is very basics of simple semantic chunking. We'll see some other popular types of semantic chunking. So first one is a statistical thresholding, also called as a cosine similarity. This is a block diagram. Okay, so let's see this theoretical part. So document is split into individual sentences, and the embedding model creates a vector for each. Okay, it measures the cosine difference between adjacent sentences and triggers a break wherever the distance exceeds the predefined threshold. So a bit of a technical point here. So basically, if you see, the sentences are split, the document is split into sentences, then create embeddings and the cosine similarity. So as we have seen, whichever sentences are matching and their similarities score is, let's say, 80%, 90%, they are clubbed together, they are set together. If the similarities less than 20% or something, they are different, right? So once they are clustered or they are grouped, then they are kept in different, let's say, packets, and then created chunks. Okay, and again the similarity score is maintained, right? So split document into sentences trigger a break when cosine similarity exceeds a predefined threshold, right? Okay, let's proceed. One more type is a statistical thresholding, also called as a co. Okay, this we have seen. Now next, buffer window or rolling window analysis. So slide through the sentences, then group into buffers, then again find the similarities, measure the similarity, and the ones which are more closer, they will be grouped together and others will be separated. And then create chunks. So slide a buffer window over sentences, compare similarity between groups instead of individual sentence, right? Okay, so next one. Next one we have max min semantic clustering. So adaptive chunking based on highest and lowest semantic similarity. So a bit of a the diagram here. So different sentences, so generate embeddings and then analyze the semantic similarities, whichever is low or high similarity, and again based on the score you put them in different chunks, and or group them or cluster them, and then you proceed. Okay, so dynamic grouping, no fixed size, auto boundary detection, and ideal for complex documentation. Okay, right. So yes, same thing what we have seen here, min max semantic clustering. Okay, now the big question is, what is the difference or comparison of these three compared to the standard recursive character in embedding or baseline? So let's see one by one. Um, Core logic, so splits when semantic similarity between the adjacent sentences drops below a threshold. uh, Groups a sliding window of sentences, okay, and dynamically clusters the sentences by analyzing the local maxima. Okay, right. Next is a best use case. So everyone has their own advantages. So best, this will be for general content with frequent but distinct topic shifts for you. Okay, for example, news, right? So news, there will be different topics. Okay, current affairs, sports, politics, business, those things. So there is a shift. That is why the statistical thresholding. Buffer, so dense technical talks or legal text where context spans multiple sentences. Okay, min max, so complex long form reasoning tasks for or agentic RAG where high coherence is critical. Okay, yeah. Then the recursive. We have again some differences. So processing cost is medium, high, low. Okay, and this is very low. Again, there is a trade-off. Okay, so parameter tuning. So high parameter tuning required, medium and low is required. Then the risk factor. So there is a risk of fragmentation. Context bleeding is a risk, and then over clustering is a risk, and then context serving. Okay, right. So now let's see some additional bonus. Uh, Okay, let's see some additional bonus. So far we have seen is all text-based semantic chunking. So now let's extend that to uh, audio processing related RAG. So audio processing related RAG. So there's a first step is to convert the sound to text. Okay, STT, different languages maybe. Okay, and then where it is useful. So timestamp aware transactions, transcription. So use a model like OpenAI Whisper with word level timestamps. This ensures that once you identify a semantic break in the text, you can map it back to the exact start and time in the audio. Okay, then speaker diarize splits, right? Integrate speaker diarization. Semantic shifts often occur when the speaker changes. Okay, let's say there's an interview, podcast, or some group discussion is happening. So assigning or identifying whether there is a shift in the talk or in the discussion is basically using the speaker diarized splits and cross sentence embedding. Okay, now also same thing for semantic chunking for image. This is different, okay, because it is not usually text based, so it is an image based, right? So we can have useful its usage in visual feature extraction. So use vision encoder to convert entire image or subregions into vectors. Semantic chunking here means grouping the images that share high feature similarity. Okay, this is important. High feature similarity. For example, all photos of engine parts, or all photos of animals, or of all photos of flowers and like that. So visual feature extraction. There, the semantic chunking is useful. Or document layout parsing, semantic object detection, and then textual visual alignment. Okay, right. So that is all about the semantic chunking. If you like the content, please like, share, and subscribe to my channel. Thank you.